have studied about refraction. We saw that light can pass through transparent and translucent materials and that it always follows the laws of refraction. How do we talk about it? What do we study for it? And why do we need to study it? Because a large number of objects around us are made out of transparent and translucent material. Then they can have any kind of boundary shapes. For example, I have a ruler here. It is transparent, refraction would take place here. If you imagine a lens that we use in the lab or the lens that we use in our spectacles, it's got a certain curvature. This is special because it's got both sides convex and the radius of curvature for both is the same. So, this is a biconvex lens. Here's another one like that, but the difference is that it is smaller in size. Its aperture is smaller. I have another lens here which has got concave sides flat over here. So, this is a biconcave lens. Different lenses behave differently and we need to study that because otherwise we can't make use of it. I have a candle, lens holder and I have a screen. We have a setup with a bench on which this lens can move. It is held vertical like this. I have a bright source. I am using a candle and the candle is lit. I am going to use a screen and this screen has two sides. On one side there is white paper and on the other side there is these big squares that are marked here. The light from here is spreading in all the directions. Some of it would fall on the lens and that is what will refract through it. After refraction and following all the rules, it is going to generate a point where all the refracted rays seem to meet. This particular point, which is created in reality after intersection of all the rays that have refracted from this lens, is called the image. Can we have a point of situation when we can catch this image? Let us take a look at that. If I move my screen here, you can see that there is this inverted flame of the candle. This is called obtained here. Why am I able to see it when I was not seeing it right now? Without the screen, I can't see this image. The reason is that the rays after refraction meet at this point and create an image from where some of them are reflected. These rays are coming to me through this line of sight and I am able to see them. But when the screen is not there, these rays go beyond and they are not stopped by anything and therefore, there is nothing that is creating this object image and I cannot see it. However, if I put my line of sight in the same line as the way the rays are coming, for example, if I put my head somewhere here, then I will be able to see the image of this flame. If I look through this lens, I will not see the flame, but I will see the image of the flame. As I stand here, I am seeing the flame. But if I go here and I have two options, one to look at the flame from here, which is the object, and the other is to look through this lens, and this will give me the image of the flame, because the rays after coming from there create the image here and those are carried to my eye. Let us proceed now to see, is there any other effect that takes place because of these two? That means, what will happen if we change the distance between or the separation between as we had seen. I am using this squared screen here, so that it is easy for us to see what happens to the image. It is inverted, it is very large. I shift this location without changing the position of the candle, and now view the image. It's become smaller. As I take this further, I will have to move my screen in order to get the image, and it is much smaller than before. If I take it further away from the candle, you get a very tiny image which is almost half the square over here on the screen. What does this mean? That the distance between the object and the lens is creating different positions where the image is formed, and second thing, it is changing in its size. The image which was formed earlier when the lens was closer to the object was very large. As we move it away, it changed its size, it became smaller and smaller. All these are real images because you have obtained it on a screen. These real images are all inverted, but they changed in their size. And what made that size change? The distance from the candle to the lens, because the screen had to be shifted in order to look for that image. So, object distance, image distance. Using these values, you can also find out the focal length of this lens. You can find out the magnification of this object. You can do several other experiments with this. But what does the knowledge of focal length give you? It will give you the application of this convex lens for many other different things in life. When you want to enlarge something, when you want to make it smaller, you can use a lens to do that. So, with this experiment, what did you learn? You learned that rays of light travel in a straight line. They follow all the rules, whether they are reflecting or refracting. In our case, refraction was taking place. Because of those rules, you had the image formed on the other side of the lens. This image was inverted. It could be received on a screen, which means that it was a real image. Real means real intersection of refracted rays after refraction. Then you also learned that the size of the image changed, and what was responsible for that was, for the same lens, if you move the object in front of it, the distance of the object from the lens made all the difference to the image. It became smaller, it became bigger, it changed its size, but remained inverted. And this effect can only be there if you understand that there is a light cone which is coming out from here. Light cone meaning the rays are converging, they meet up at the image and go beyond. If you placed your eye in the light cone, you could see the image, but you cannot see the image from anywhere else. That also you saw. So, this gives you a simple idea about the lens, and you of course know that we did this to understand the behavior of lenses, so that we can use them in daily life.